Hello, everybody. I'm Andrea Pellegrini. I'm a distinguished engineer within the infrastructure line of business, and my role is to look after performance and workloads for server and networking at ARM. One of the big challenges that I had when we started looking at cloud server workloads and data center workloads from ARM is that we didn't really have any foothold in the market. I started here about 6 years ago, and really one of the things that we started to do and we had to do was develop a methodology and a way of thinking and a way actually of measuring performance, assessing where our machines were, what we could have done to make things better, how our competitors landed, all that kind of good stuff, with systems that were just very different from what was in the market at that point of time. Different architecture, different microarchitecture, different core counts, different capabilities to change frequencies, all that kind of stuff. And what I wanted to do today is share a little bit of things that we learned along the way. So let's start actually with giving a little bit of a description about ARM, why ARM in the data center, and all that good stuff. If we really have to look forward in a project where we think data centers and in general the whole digital infrastructure that sustains actually our lifestyle is going to go, is quite likely that we're going to see a world where we have more than 1 trillion of devices connected together effectively. These actually may be IoT devices that are in the field, could be actually edge devices that process data as it goes through, and also actually cloud data centers in big actually cloud providers or such. And really actually we see ARM as a good architecture to really scale from the smallest devices that are actually battery operated and energy limited, all the way down into high performance cloud data center systems. And as I said, my focus has been mainly actually on that hand of the spectrum. A little bit about ARM. ARM does not produce silicon. We do not actually sell parts that you can buy directly. We have some few test chips that we provide to selected customers every once in a while, but in general we only provide the architecture that is needed actually to design systems in case actually partners might want to do so, or IPs that they can take and integrate in their SoC. Example of IPs that we developed are the Neoverse cores in the infrastructures of server and networking market. You might be familiar also with the Cortex class of products that are actually more popular in mobile and client. Beyond the cores, we also provide all the system IPs that are needed to really actually put together many of the components of an SoC. So coherent mesh, such that you can connect all different cores together, but also the interrupt controllers, MMU units, ways actually to control power, security, all that kind of stuff. There's a number of things that we do not do at ARM. We do not design memory controllers anymore, or root ports and PCIe root complexes. So those are things actually that are generally provided by third-party vendors. In general, what ARM focuses on is on, as I said, developing the IPs actually that people can use in their SoC, but also in developing common architectures and platforms that can be used to standardize effectively how software looks at a system and in general the architecture. Let's look a little bit about our roadmap. So these are slightly dated. We are now in production actually, or in pre-production with some of the V1 and 2 platforms. But in general, we've been on this journey for a few years, and we're starting to build a pretty interesting roadmap of cores and system IPs. This actually spans on 3 different series of products. We have the V series, which is the high performance cores that really actually start to beef up vector capabilities, but also actually the size of the cores themselves are actually pretty wide and very very powerful cores. We also have the N series. That's actually what we started with. That's an extremely efficient but also high performance line of products. N1 has been deployed by Ampere in their Ultra platforms, as well as by AWS in their Graviton 2 systems. We have a new generation of systems, which is N2. These are actually starting to show up in silicon as we speak. And finally, we have the really high efficiency series, which is actually the E series, which we only have one product at this point of time. There's going to be more as we go, but these designs are really targeting systems where the most important thing is actually efficiency. So they are, for instance, E1 is in order, multi-threaded, and all that kind of stuff. It's dedicated to a certain portion of the market and covers that really well. Okay, just to put a little bit actually things in context. Again, this slide is slightly dated. I didn't want to update it actually with new designs that are coming up from partners today, since those are still they're not generally available yet. So let's talk a little bit actually on the older generation and what we've seen so far in the market. We see extremely good performance as well as utilization for these designs. What we hear actually from customers in the field is that they can achieve up to 40% higher performance on general compute, more than 25% increase in performance on the video encoding. Sometimes the ADA and simulation tools perform more than 50% higher compared to our competitors. So actually for web servers and key value databases, we also achieve a very very significant performance scores for SpecGVP. So in general, these machines are doing really well, and to be honest, they're very well balanced between what you can achieve in terms of integer performance per thread compared to integer performance per socket, which are both metrics actually that we really care about. Very briefly, again, I'm not going to go too much into the detail on this, but we see actually there is quite a bit of adoption of these designs in the market. And AWS has been one of our key customers in the past few years, continues to be. And we see that a lot of the new instances that they've been pushing out into the market are actually based on the Neoverse designs and on that line of products. So they're all ARM-based. So what I'm saying all this, you might know actually of ARM as a company that works on mobile phones or the small devices, all that kind of stuff. Well, we're actually starting to become a fairly significant presence in the data center as well. So thank you for inviting me here, and thank you actually for allowing me to explain a little bit actually some of our experience actually. And going back actually to the topic for the day, what I wanted to cover is how we think about performance. Now, these equations are nothing new, right? They're basic equations. They're some of the first chapters of the Hennessy-Patterson. So just let's review them real quick. And what I wanted to do is actually dig a little bit more into these equations step by step for the things that actually matter for when we change so much in the systems that we're comparing. So let's start actually with the basic. What we are looking at when we compare different machines is effectively the time that these machines actually take to perform a certain task. The task has to be the same, and we have to measure it actually in the same way. Now, how do we split actually what happens in the system? Well, first of all, we need to consider what are the instructions that are used in order actually to describe this task, right? So the task is going to be a program. What are the instructions actually that go in? Now, between CISC and RISC architectures, So ARM is RISC, x86 is CISC. There are quite a few differences, and that actually can change things depending on how you look at them. So we're going to look a little bit about that. Next thing is how many instructions we can execute per clock. This is actually what is also called IPC. In this case, actually, is clock over instructions, so is the inverse, is CPI. We will also dig a little bit more into that. And then the last one is effectively frequency. So is how many clock cycles we can perform per second. In this case, actually the inverse of frequency, but you got the point. Now, if you're familiar with benchmarking and measuring performance, you're probably familiar with spec CPU. And spec CPU matches these equations very, very well. This is because spec CPU is effectively measuring how long it takes to perform a certain task. This task is very well defined. There is a beginning, there is an end. Everything is great. You can just measure the time, wall time on that. We're good to go. If you improve any of these things by a certain amount, you're probably going to see actually a fairly good correlation with what you measure on spec, with some caveats, but in general that is true. That's very different actually for data center workloads. There are a lot of similarities in way of thinking. I hope I can actually discuss some of them today, and I hope it actually makes sense. But I want to leave this caveat here. Data center workloads are trickier, and let's get to that actually after a few slides. All right, so let's start actually with the first component of the performance equation, which is instructions that are needed to map actually a task into a certain problem. As I mentioned, ARM is our RISC architecture, is very RISC. Now we're making some changes there. You're going to see some interesting instructions in the next ISA revisions, but in general, all instructions are 32 bits, so there is no variable size. That's actually very nice for certain purposes, but also means actually that sometimes you actually take more a larger memory footprint to encode the same program. We always have to go through registers, so it's a purely load and store architectures. We have no way to do in-memory operations, or what it will look from the ASA as memory operations, such as add to this piece of memory, to add to the value in this piece of memory, the value in this register, and store it back into this memory address. We don't have anything like that. In general, the instruction count that you could see if you just look at instructions run, because of the RISC nature of the architecture, in general actually drives higher instruction counts for ARM. This does not mean that performance is lower by any means. And in general, the way we look at comparing x86 versus ARM is by looking at x86 macro operations versus ARM. There's a much closer actual correlation between those two. Finally, ARM implementations can either fuse or split instructions. That's also true for x86, obviously. There's a lot more x86 instructions that split. There's also actually a few cases where we fuse them. Currently in our course, we only actually fuse them. We do not split. Additionally, the ARM implementation, the ARM architecture, can also be implemented by in different ways. So some of these microarchitectural choices actually could differ from one implementation to another. So I want to highlight that because sometimes actually things actually could look a little bit different. Finally, ARM is a relaxed memory model. So you will actually you will see some memory barriers, quite a bit more actually that you would require in x86, and these actually can be quite expensive as well. We did a lot of work to improve them, but generally you will see quite a bit more of them, and that's something to watch out when you're looking at performance and when you're looking at what are the impact on performance on some of these things. Another thing I want to mention is that because our instructions are fixed size, oftentimes we end up with larger code footprint than x86, and what we've seen is that in quite a few cases we end up with better performance if we optimize the code for size instead of actually performance. So, you know, minus OS sometimes actually can achieve a higher performance than, you know, O3 or O2. Couple other things when comparing different ISAs, it's also important to make sure that we're looking at features and enabling features that are similar as much as possible. What I mean by that is that, for instance, x86 had atomic operations for a long time. The way you do them is basically by having a lock in front of your exchange, which does a atomic compare and exchange. That's just an example. We didn't have those kind of operations until the version 8.2 of IRSA. And because of that, actually, some of the software that is out in the field does not actually use those instructions. So we roll back actually to the old RISC way of doing atomics, which is by splitting the operation between a load exclusive and a stored conditional pair. That works fine for low core count systems. In high core count systems, that's not great. So again, when you compare different systems, make sure actually some of these features are enabled, because otherwise you might end up fooling yourself and not really looking at everything that these machines put on the table. Another thing I wanted to mention is that vector length is quite significant for certain. The difference is quite significant, and that actually could impact performance quite a bit for center applications. Because of that, actually, it makes sense to actually look at what the code does and whether those type of instructions are there. If there is a piece of code that uses a lot of AEX512 instructions and does really well, doesn't really suffer too much from the frequency drop and all that kind of stuff, you know, you might actually end up getting a performance hit if you move to a system that doesn't have the same firepower instead of vector length. CPI. So the second factor in our equation is clock cycles per instruction. CPI is great. Sometimes actually we go by IPC. I'll try actually not to confuse them as I speak, but you know, hopefully things are clear as I go. The way our roadmap is currently developing, we are really actually starting to have fairly large machines. Graviton 3, for instance, here widened the front end by a substantial amount and also actually doubled the back end. So these are very, very wide machines. They're actually wider than the equivalent x86 cores for the same generation. We also have quite a bit larger L1 caches. So we have 64 kilobytes of data cache and dedicated instruction cache. This is because actually we do virtual indexing, physical tagging of our level 1 caches. So all these things actually really allow you to reduce your CPI, hence increase your IPC. So that's something these are some of the levers actually that we play to keep improving performance. Why do we do that? This is because typically widening the cores is often more energy efficient than increasing the frequency. And if you look at where we are, I'm going to talk about it in the next slide, we tend to run our systems at a much lower core frequency. SMT, so simultaneous multi-threading, this is also something that impacts IPC. In general, if you have multiple threads working on the same core, you're going to have an overall increase in core IPC. And this actually can be very useful for some workloads. We do not do that, so we do not actually enable SMT in our V or N series of products. And this actually is for two reasons. First actually makes our designs simpler, so they're easy to validate. They don't really have to deal with a lot of the issues actually of synchronizing things and all that kind of stuff. So it just makes life simpler. We can actually have a roadmap that where we can actually push products actually faster out. Additionally, this is something actually that some of our customers really like, because when they deploy these designs in their cloud instances, they can effectively sell dedicated cores, L1 and L2 caches for their customers, for the software running. And that's something that is a lot of the customers really like. But then again, if you look at this factor, you might actually need to figure out how SMT impacts your performance for your workload, and how actually you enable or disable this feature depending on what you're trying to measure and test. All right, the third piece of the equation is frequency and turbo. So I wrote here actually just a quick equation that determines how we generally compute power in the industry. That's a multiplication of alpha, the activity factor for the core, C9, that's the capacity that gets actually switched whenever there's activity in the system. Then there's frequency, and then there's a factor of voltage square. There's a half in the middle because there's an integral, so that's how you end up actually with that constant at the beginning. So why does this matter, and why does this equation actually matter? Well, when you're trying to improve frequency, you effectively end up raising linearly this equation through f as you increase frequency, but you also often have to increase your voltage, and that actually grows quadratically. So that actually matters a lot. Power consumption and cooling of an SoC, it keeps growing. We were actually at 150 watts a few years ago. We moved to 200. We're into 250. We're going to soon be in the 350 to 400 watts per SoC in a data center system, and that number really determines how many cores you can pack in one SoC and at what frequency you can run them. So power is what determines effectively how fast you can clock your cores. Our designs, they can push actually pretty high in frequency. They can, we design them such that they can go all the way up to 3.5 gigahertz. However, most of our partners don't actually go that high, and we definitely don't go as high as some of our competitors in the x86 world. Why is that? Well, makes things easier in many ways. So we can basically design our systems where they can be the most efficiency at a design point and a frequency and voltage level where they can actually maintain a sustained level of performance and be very efficient. We also avoid actually jitter from noisy neighbors, and frequency change is actually due to activity in the system, people using vector units, all that kind of stuff. That said, turbo can help certain classes of workloads, right? So if you are, for instance, creating a web page for like an e-commerce database, you might actually have a number of requests that go out, fetch whatever you need from the database, bring the information back, and then you might actually have a thread that puts everything together and create actually a web page to send back to the customer. That last phase, it is not parallelizable, and if you can actually just blast through a core that can go very fast, you actually might have an advantage. But that said, we're very happy where we are, and what we did actually makes sense. That said, it is something that you need to keep in account, right? So if your parts actually go up and down in frequency, all that kind of stuff, how you really think about that, and what can you do to either control that for your measurements or monitor that actually does matter a lot. All right, in terms of performance in the real world, as I said, everything we said still applies, right? So instructions that are run, how many instructions, what is your CPI, what is your frequency, all those things actually matter. The challenge is that you no longer really run on a certain task and trying to speed it up as much as possible. Oftentimes, what you end up doing in the real world is trying to maintain a certain level of throughput within a certain SLA, service level agreement, which is like a latency, basically, of how long it would take for the request to come back. It matters a lot because when you have MapReduce task, which happens very often at the data center, how long it takes actually for this task to complete is the equivalent to the latency of the slowest request coming back. Additionally, there are ways actually to maintain performance as your workload increases, oftentimes by actually replicating the resources and sharding actually your database or whatnot. So in general, one thing that we learned doing our experiences is that when you're comparing systems that are very, very different, in situations where latency matters, where the throughput matters, all that kind of stuff, one thing that is also worth normalizing oftentimes is actually the amount of work that gets done. So basically try to run your test on two different systems with loads that it can both sustain such that they don't get overwhelmed, and really look at the time actually to spend doing that. That's often actually a much better way to measure what the different machines are good at compared to just pushing to the limit and see what happens there. That often makes the measurements very, very noisy and very, very confusing. In conclusion, so what we are seeing, and actually that's thanks to a lot that has been happening in the industry, including actually some of the work that we've done and some of the products that we put out, current systems actually look all very different from each other. System architectural difference, cache sizes, the way caches work, core count frequencies, do they have multi-threading or not, why I say they have. There's a lot of like different things actually come into play. It's going to be even worse, right? Accelerator is going to come and make things even more heterogeneous and more complex. The disaggregated memory is going to come in and make things even more complicated. It's going to be a much more interesting world, but also a lot more complicated to measure and assess. In general, the rule book that we described originally still applies, right? So those equations are still valid. These are still actually the golden rules actually on how to measure performance. What really matters is how can we really normalize on the things that matter, create baselines that make sense. How do we make sure that we measure things that matter to the user? Sometimes it's not, as I said, necessarily how long it takes. Sometimes is what is the tail latency for this request to come back? What is the throughput under SLA? There's a lot of other metrics that are worth looking into. And as I mentioned, if you're studying scaling factors or features in particular detail, try to normalize as much as you can, including actually how the workload is behaving. That can actually help a lot. Just help understand what is happening in the machine, as I said. And also, if you're just comparing the different systems just as they are out of the box, just make sure that you try to extract most of the performance from the features that are there, the capabilities that are there. So don't limit actually the systems just because one machine might have one feature, the other one might not. Your users don't care. The users actually will use whatever is there to get the most out of these boxes. Before I leave, and I leave some room for questions, I wanted to send some links here for just actually some of the machines that are out there that are based on our designs, and they're really, really cool systems. And if you haven't played with them yet, please do so. There are a handful actually already in the States available at AWS and Oracle, more to come, I can tell you that. And then there is also Alibaba Cloud in China. Thank you very much. I'll be happy to take any questions.